Good day and welcome to another class. So today we'll be looking at motion. Alright. The world is full of things in motion, from things smaller than our eyes can see to things as big as planets. I'm sure we know even the earth we live in is in a state of constant motion. There's a saying I read once, to be ignorant of motion is to be ignorant of nature. Therefore, if we actually want to have an understanding of nature, we must understand completely the intricacies of motion. So, motion can be described as a change in position of an object with respect to time. Okay? And the study of motion of bodies or the forces that produce motion is called mechanics. Okay? And this is usually divided into two kinds. Alright? We have kinematics and we have dynamics. Okay, so the study of motion of objects without regard or any form of reference to the forces that cause it is called kinematics, while the study of forces and how they affect motion is called dynamics. Okay, so through our existence, we must have noticed different objects move in different ways. Okay, we've seen cars move, we've seen roller coasters, okay, in fun parks, we've seen the movement of children on a bouncing castle, we've seen butterflies in motion. Okay, so motion has four basic classifications, alright, and they are translational motion, rotational motion, we have oscillatory and vibratory motion, and then we have random motion. Okay, so these are the classification of the different kind of motion that is possible. Okay, the different kind of motion you've experienced can be classified into these basic four types. Let's talk about the first one, translational motion. It's a motion in which all points on a body move uniformly and in the same direction. Okay, so what it's trying to say is if we have a body, let's say we have this shape moving in this direction, alright, now every point on this body, every single point on this body will move in that same direction. Okay, alright, if that happens, then that's translational motion. Translational motion can be divided into two parts. You have the rectilinear motion and the curvilinear motion. Okay, now the rectilinear motion is linear motion, all right, is motion in a straight line, while the curvilinear motion is motion in a curved path. So what we're saying in essence is the rectilinear motion is motion in a straight line like this. So this object might be moving just on a straight line in this direction, alright, and it is one dimensional. When you say one dimensional, it happens if you have, let's say you have this axis like this, alright, it being that one dimensional is you can represent it on just one axis of, let's say this is your y, of course, like your y axis on the Cartesian, and this is your x. Okay, so you can represent the motion of this object in just one axis, and once that is possible, it is one dimensional. Okay, but for the curvilinear motion, it is usually two dimensional. All right, so for two dimensional motion, it means you can't represent the motion in one axis alone. Let's say, for example, this is a car and it goes around a bend. Okay, let's say, or this is a roundabout, and this car goes around this roundabout like this. Okay, now this is not a one-dimensional motion because you can't describe this with a single axis. You need both axes to describe this kind of motion. This is us like looking at the car from above. Okay, so this is the roundabout from the plan view, and this is the car taking the roundabout. Okay, so if we want to represent this, if we take this to be our axis, okay, the x and y, you will see that, of course, this representation cannot make sense on one axis alone. Okay, so if we have this kind of motion of an object, okay, you can see that for us to define this, we need to know its positions in the y-axis as well as in the x, right? Okay, to properly define this motion. So you see, it's a two-dimensional motion because we need both axes to define it. While for just an object moving on a straight line, all we need is one axis. So let's say, for example, these are x and y, and the car just moves in a straight line like this, you see, what we need to know is its value on this axis, and it can be properly defined. So the curvilinear motion is a two-dimensional motion, and the rectilinear motion is a one-dimensional motion. So an example of a one-dimensional motion is a car that moves in a straight line to its destination, or the motion of an elevator. Okay, an elevator can go upwards or downwards alone, and that is motion in a straight line in one direction. Okay, so you have the motion of a sliding door. It can move towards the left or towards the right. It can't go up or down. When you have a sliding door, it can't go up or down. So those are one-dimensional motions. They can be represented with one axis on a graph. Okay, so this change, if represented in the Cartesian coordinates, occurs in only one axis, either the x or the y. Okay, so this is an example. A man walks 5 meters eastwards. Okay, so you can see he starts from a position 0 and walks 5 meters eastward. All right, the change in y here is 0. There's no change on this axis. Okay, while the change in x is 5 meters. So you can see that a two-dimensional motion is motion across a plane or a surface. All right, so an example is a mouse moving on a table surface. So okay, so let's say these four corners, the four corners of a table, and then this motion is the motion of a rat on that surface. So you can see it's two-dimensional because you can't describe it only on one axis. You will need both axes to define it. So this is usually a two-dimensional motion, is usually a motion on a surface, okay, a plane or a surface. All right, while we have the three-dimensional motion to be a motion that has change in just not the x and the y axis alone, but it has change in all three axes. You have the x, the y, the z axis. Okay, so this is the kind of motion that happens in space or in air. All right, so understanding this kind of motion is, okay, let's say we have this. Okay, all right, so we have our x, y, and z axes. Then you see that, if we take for example an aeroplane flying, you see an aeroplane can fly. An aeroplane can actually fly in any direction. It can go this way. It can actually come like this. It can go like this. So this is what a three-dimensional motion is like. Okay, so you can have something like this box. So you see you have that space. So you see how the motion can occur within the three dimensions, okay, not just one or two dimensions. So this is what you have for a three-dimensional motion. An example of a three-dimensional motion is an aeroplane flying in the sky, a flying butterfly, and so on and so forth. So an easy way to remember this is a length is one-dimensional, a square is two-dimensional. Of course, you know this is more like a surface. All right, it's more like a surface, while a cube is three-dimensional. Okay, examples of linear motion includes a man walking in a straight line, a fruit falling to the surface of the earth from tree. Okay, so if you have a man walking in a straight line like this, that's linear motion. You have a fruit falling this way from a tree, linear motion. Train moving on the straight line track, linear motion. Examples of curvilinear motion: running on a curved track. Right, roller coaster rides. You have ball thrown that follows a parabolic path. Okay, when you have a ball thrown, it follows this kind of path. All right, and this is what is referred to as the parabolic path. Okay, so the ball follows this kind of path and then lands back on the floor. So it's an example of curvilinear motion. All right, okay, so let's move on to rotational motion. Rotational motion is the movement of a body around a circular path in a fixed orbit. All points on the body in rotational motion move in concentric circles. So if we consider the points on this disc, this A and B is us picking two random points on this object or on this disc. All right, so we can pick any other point on the disc, but you see that these 2 points in rotational motion are moving in concentric circles, which means the full body is moving a circular path, and every single point on that body moves in that same circular path. So once we have a thing like this, we know we're dealing with circular motion. Okay, so we have oscillatory and vibratory motion. This one's a to and fro movement of a body about a fixed position. So it's more like you have an object like this. Let's say you have an object like this, fixed in space, okay, or fixed wherever. All right, this object can't move except to just vibrate about the main position. It can move, let's say, left and right slightly. It can slightly move like this, left and right, without leaving this fixed position. So that to and fro movement of that body is what you call the vibratory motion. It can also be referred to as the oscillatory motion. All right, it's a kind of motion that repeats itself. It reverses the direction of its motion and returns regularly to its starting point. Okay, so you can see that it moves to this side, it comes back, moves to this other side, comes back, and that motion keeps repeating itself. It's periodic, all right, because it's repeated in equal intervals of time. Okay, so an example is the movement of a simple pendulum. Of course, I'm sure we can relate with the simple pendulum. It's usually a ball and then hung by a string like this, and so it has the ability to swing this way or this way. Okay, so that's basically what the simple pendulum is like. Okay, we have the vibration of a string on a musical instrument, maybe a guitar, right? Once you strike it, you see it's fixed on both ends, but it can move up and down, up and down. That's vibratory motion. It can't leave that fixed position, but it can just move slightly upwards, downwards, and that motion is repeated continuously until the influence is dead. Alright, so random motion is the motion of an object with no specific path. Objects move irregularly and disorderly with no specific direction. A classical example is Brownian motion. Okay, so Brownian motion is the random and irregular motion of a particle suspended in a medium, maybe water, gas, air. Alright, so an example of this Brownian motion is what you have with smoke particles. Okay, so you're burning fire and you see the smoke from the fire moving in every direction, just moving randomly, an irregular motion, it's just everywhere. Okay, so that's a classical example of Brownian motion. Okay, so understand that this course is basically trying to make you understand motion and its classifications. So as you move around and you live your normal everyday life, just try to classify the motions you see, the different movements you see. Try to classify them into these different kinds of motion. It will help you relate with your environment better, help you understand your environment better, and help you solve problems that are related to motion better. Okay, so that's the advantage this course is actually trying to achieve with you. Okay, so relative motion is the motion of an object observed with respect to another object in rest or in motion. Okay, so when you say relative motion, it means a motion compared to another. You're considering the position of this object with respect to time. Okay, but you're making that consideration based on the position of another object with respect to time. Alright, so that's what relative motion means. Okay, so what normally motion is relative in nature. Okay, and that is because you can't actually relate in motion if you and what you're observing are in the same position at the same time interval all the time. Then you would not see any difference. For example, if you're in a car and I'm standing on the road and you drive past me, obviously I will know you moved. I would be able to relate to the fact that motion just happened. But what if you're in a car, I'm in a car, the same car, driving at the same speed, but we don't get to maybe see the outside world to realize motion is taking place. We don't get to feel vibrations, we don't get to hear any noise to make us know motion is taking place, but motion just happens smoothly and calmly. I will look at you, we'll be discussing, having a conversation, but I will not be able to relate to the fact that you are moving, because I'm also moving at the same speed, at the same pace, under the same conditions. Alright, but if I was outside that frame and maybe I was standing on the road just watching, looking at you make that same change in position in the same time interval, I would realize you are moving. So you see, motion is actually relative in nature. Okay, so speed is the rate at which a body in motion covers a distance. So speed is actually distance over time. Okay, that's the formula for speed, right? Uniform speed is covering the same distance at equal interval of time. Okay, it can be referred to as constant speed. No change in distance covered and no change in time spent in covering the distance. So let's say you're traveling and I decide to observe your motion, and I check your first 5 minutes. I noticed you covered 3 meters. Okay, and I check your next 5 minutes and I notice you covered 3 meters. And I check the next 5 minutes, that's 15 minutes now, but the next 5 minutes, I notice you covered same amount of distance. Okay, it means you're moving in uniform motion. Okay, your distance covered is consistent with the time interval. So that's uniform speed. All right. Velocity is the rate at which a body in motion covers a given distance. Okay, velocity is similar to speed. The only difference between speed and velocity is that velocity has to do with direction. You have to have a clear direction for it to be velocity, but speed can be in any way, in any direction. A butterfly has speed. Okay, it just travels, flies here and there. But a bullet shot has velocity. Okay, because it just moves in that direction it was shot. Okay, so velocity is displacement over time, and you know the difference between distance and displacement is also direction. So uniform velocity is constant velocity. There's no change in time spent in covering equal displacement. All right, so let's move on to the time graphs. So let's say we have a graph, okay, with this place representing distance, okay, and this place representing time. All right, so, and let's say we have an object that moves in a straight line. Okay, all right, let's assume this is a straight line. Okay, now since this is a straight line, it will mean that we're covering the same distance at equal time intervals. A straight line like this on a distance time graph represents uniform velocity. Okay, so to find the speed of this graph, to find the speed of the object from this graph, we would have to find the gradient. And you know, finding the gradient is finding the change in the value of the quantity in the y-axis divided by the change in value of the quantity in the x-axis. So if we do that, we find the gradient. And you know that, of course, this y-axis represents distance and the x-axis represents the time. So if we're finding the gradient, it means we're going to be finding distance over time, change of quantity in the y-axis, which is distance, over change of the quantity in the x-axis. Okay, so that's how you find the gradient for this kind of graph. Okay, so you can see here we have speed to be dA over dc, which is the gradient. So this is your dA. Okay, that's a change in the displacement, all right, divided by the change in time, which is dc. Okay, so if you have a straight line graph like this, it usually denotes uniform velocity or uniform speed, all right, because this goes to show that you are covering equal distances at equal time interval. Okay, that's the only reason why you would have a straight line graph. If you're not covering equal distances at equal time interval, you're not going to have a straight line graph, okay, in a distance time graph or displacement time graph. Okay, so if the graph is a curve and we are asked to find the speed or the velocity, okay, it means we're going to find the gradient at a particular point on the graph. All right, first of all, once you see a distance time graph or displacement time graph and it's curved, you just know automatically that it is not uniform motion. All right, so you can't really find the velocity of the bulk. What you can find is the instantaneous velocity at a particular point in time. Okay, so you just pick a point on the graph and then you find the velocity at that point, at that particular time of the motion. So we're taking point B here. Okay, so to find the velocity at point B, okay, we find the gradient of the tangent at that point. So you're going to have to draw a tangent at that point, a line that coincides with the curve, and you now find the gradient of that line. So we have FE here over AE. So that's the change of the quantity on the y-axis divided by the change on the x-axis. So we have FE over AE to give us the instantaneous speed or the instantaneous velocity, depending on if it's a distance time graph or a displacement time graph. Alright, so acceleration. So acceleration is the rate of increase of velocity with time. Okay, so of course the formula is change in velocity over time, and we have deceleration or retardation to be the opposite of acceleration. Alright, so it's the rate at which velocity decreases, and acceleration can also be gotten by final velocity minus initial velocity over time, which means you have an object, and let's say that your object moves from this point in space to this point in space, all right, at different velocities. So what we can do is find the velocity at this point, find the velocity at this point. So at this point, if it started from rest, the velocity here can be 0 meters per second, and the velocity here, maybe it's moved up to 5 meters per second. So your change in velocity here will be, your acceleration here will be final velocity, which is 5, minus initial velocity, which is 0, divided by the time it took to complete this motion, the time interval between these 2 points. Okay, that would be your acceleration. Okay, so uniform acceleration is the increase in velocity at equal amounts of time. Uniform acceleration is the increase in velocity by equal amounts, all right, when you consider it at equal interval of time. Okay, so it's quite similar with the one for velocity, except for the fact that in this case you're not considering change in distance. Okay, you're not considering change in distance with respect to time. You're considering the change in the velocity of the object in motion with respect to time. Okay, so let's consider the velocity time graph. So normally we can get acceleration from the velocity time graph easily. Okay, and one way to do that is to find the gradient of the graph. Okay, but then you can have a complex situation like this one here, where you have a straight line, okay, at an angle, and then you have a straight line like this horizontally, and you have another one here at an angle. So in this situation, this line AB represents uniform acceleration, which means the velocity is changing at an equal amount when you're considering an equal time interval. Okay, so that will give you uniform velocity, and if you represent it on the velocity time graph, you're going to have this straight line graph. Okay, now BC represents no change in velocity. The velocity along this line remains constant, it doesn't change. It's just one velocity from B to C, and that represents constant velocity. The velocity is constant. While here we go back to having uniform, but not acceleration this time, but retardation, because retardation is the opposite of acceleration. So you can see that the change in velocity occurs, but it is occurring negatively, like it is dropping instead of increasing. Here velocity increases, here velocity drops, it reduces, and so this is retardation happening here. So uniform retardation. Okay, acceleration for AB, if you want to find the acceleration for this part, you find the gradient of the curve, and that will be change on the y-axis BE over AE, which is change on the x-axis. Okay, so if you want to find acceleration for BC, there's no point because there's no acceleration there. We can also find acceleration for CD, or the retardation for CD, which would be CF over FD. So that will be us finding the gradient from that graph. So if you have a graph that has curved lines, okay, it will show that the motion of the object you considered has an irregular velocity, knowing that we're considering the velocity time graph. Okay, so if you have something like this, you have a curve, we know that there's variable acceleration here. Okay, so in that case, to find the acceleration of this, we can find the instantaneous acceleration by finding the acceleration of a given point. Okay, Now, if we take point P here to be where we want to find, or the point whose acceleration we want to find, okay, we can find that by drawing a line tangent to the curve. That's a line that coincides with the curve, and then find the gradient of that line. So you can see here we have CE, change in the y-axis, over DE, change in the x. Okay, so that will give us the instantaneous acceleration at that point. Okay, so let's move on to distance, finding distance from the velocity time graph. So if we have the velocity time graph like this, our distance can easily be found by finding the area under the curve. Alright, we can actually find the area under this curve by splitting it into known shapes. So you can see here we have a triangle here we have a rectangle here, and here we have another triangle here. So to find the area of this curve, we find the area of the individual shapes. So the distance traveled in time AE will be half AE times BE. We know the area of a triangle is half base times height. So our base is AE and our height is BE. Then to find that for EF, we find the area of the rectangle, which is BC times CF. Of course, BC is one length, CF is the other length, and we know that the area of rectangle is length times breadth. Both of them represent lengths, but different lengths of the object. So that's the same thing we do here. Then we go back to still using same formula for area of triangles to find the distance traveled during retardation. So we have half FD times CD. Alright, so what we now do is to sum up all the areas we got, all the values we got, and that answer we get from that will be the distance covered by the object in motion. Alright, so we move to equations of uniformly accelerated motion. So once we have uniformly accelerated motion, there are certain vital formulas that are very essential for us to have, okay, as to have in our toolkit for us to use to solve problems, okay. And one of them is V equal to U plus AT. All right, and the second one is S equal to UT plus half AT squared, and the third one is V squared equal to U squared plus 2AS. Okay, these formulas are formulas that have been properly derived. Okay, we are not going into the derivation here, but these formulas are what you need to solve uniformly accelerated motion problems. Okay, U here represents initial velocity, V represents final velocity, T represents time, S represents distance, A represents uniform acceleration. So wherever you see them in this equation, this is what they represent. Okay, remember, a uniformly accelerated motion is a motion whose velocity changes, okay, at an equal amount over an equal interval of time. So let's say I observe the motion. The first 5 minutes of the motion, the change in velocity is 2 meters per second. That means maybe the object drove from 0 meters per second to 2 meters per second in the first 5 minutes. In the next 5 minutes, the object drove from 5 meters per second to 10 meters per second. In the next 5 minutes, the object drove from 10 meters per second to 15 meters per second. So if you check the change in velocity in the 3 different time intervals I considered, of course, the time intervals were the same, 5 minutes. If you check that change in velocity, you will find out that it is equal over the time intervals I checked. So you have 5 meters per second change in velocity throughout the 3 different instances. Now that is uniformly accelerated motion. There's an acceleration taking place from 0 to 5, 5 to 10, 10 to 15, but then it is uniform. Okay, so when you have that kind of motion, these formulas will be very effective in solving their problems. So you would agree with me that gravity offers uniform accelerated motion to objects. So for motion under gravity, when an object is thrown up, it experiences retardation due to the action of the force of gravity acting on it to pull it back to the earth. Okay, the object will gradually lose speed until it comes to rest briefly at a height. Alright, so if you check, this object at this point is thrown upwards, and at this point you see its velocity is maximum, but as it continues to go up, that velocity drops until the object gets to a point where the velocity is completely gone. You have velocity at 0, and at that point it begins to fall back down to the earth, and in this case its speed gradually increases. Remember, going up the speed reduces, coming down the speed increases. So it's more like you have retardation going upwards and you have acceleration coming downwards. Okay, and the reason why this velocity increases is due to the force of gravity on the object. All right, that influence of the acceleration due to gravity is usually valued at 9.8 meters per second or 10 meters per second approximately. Okay, I think for this course we'll be using 10 meters per second to solve problems. Okay, so when we need to solve problems based on gravity, we change this formula to be like this. So our v will be normal, will be same, which is final velocity. Our u will be same, initial velocity, but our acceleration will be different. Okay, because the acceleration we're considering in this case is now the acceleration due to gravity, so we'll change our acceleration to g. All right, same thing with the second equation. Our acceleration will change to g, but then our s, which is our distance, will change to h, which is height, because in this case we're actually considering height, so there's no point just writing distance there when the only distance we're considering under gravity is height. All right, so the same thing with the third equation. All right, distance changes to h, acceleration changes to g. Okay, so we have this to be what all these initials mean. Okay, so what changes here is h for height and g for acceleration due to gravity.